Hello friends, a warm welcome to all. Today in this video we are going to discuss natural coordinates in two dimensions. Before starting the discussion, we should have a clear idea about natural coordinates. What does it means? Natural coordinates are non-dimensional numbers that can be used to represent the position of any point on a particular element by manipulating it with non-nodal values. What does it mean? For example, consider a one-dimensional element with endpoints A and B. Let x1 and x2 be the global coordinates of points A and B. It is non-nodal values, that is x1 and x2 are here non-nodal values. If we want to find out the location of any intermediate point P between A and B, we have to first define the set of natural coordinates at point P, that is L1 and L2. Then the location of P x is given as L1 x1 plus L2 x2, where L1 and L2 are the set of natural coordinates and x1 and x2 are the non-nodal values. Along with that, we have to notice there is a relationship between L1 and L2. The sum of L1 and L2 is 1. That is, for a one-dimensional element, the sum of two natural coordinates is 1. We get two equations and we have two unknowns. Here the unknowns are L1 and L2. By solving these two equations, we will get an expression for L1 and L2, which are not constants but vary with respect to x. Now we can advance our discussion to natural coordinates in two dimensions. For that, consider a triangular element ABC whose coordinates are A x1 y1, B x2 y2, C x3 y3. Let P be an arbitrary point within that element with coordinates x and y. L1, L2, L3 are the natural coordinates at the point P. From the definition of natural coordinates, we know that L1 plus L2 plus L3 equal to 1 and the position x is given as L1 x1 plus L2 x2 plus L3 x3 and the position y is given as L1 y1 L2 y2 plus L3 y3. Why here two coordinates are coming? Because we are dealing with two-dimensional element. In order to specify the displacement and other properties of a two-dimensional element, we will require two coordinates. Here we have three equations and three unknowns. Here the unknowns are L1, L2, L3. We can solve this set of equation and find out the solutions for L1, L2, L3. For that, we can represent the above equation in matrix form, which will give 1, 1, 1, x1, x2, x3, y1, y2, y3 into L1, L2, L3 equal to 1xy. Here we want to find out the value of L1, L2, L3. For that, we have to multiply with the inverse of this matrix with both LHS and RHS, which will give us L1, L2, L3 equal to 1, 1, 1, x1, x2, x3, y1, y2, y3, the whole inverse into 1xy. Here we want to find out the inverse of a 3 by 3 matrix. What is the procedure to find out the inverse of a 3 by 3 matrix? We have to find out the transpose of cofactor matrix and the determinant of this particular matrix. Then the inverse is given by the ratio of transpose of cofactor matrix to the determinant of this particular matrix. Okay. What is cofactor matrix? Cofactor matrix is a matrix in which the cofactors of each and every elements of this matrix is arranged. What we mean by cofactor? Cofactors are signed minors. What are minors? Minors are the determinant obtained by eliminating the row and column containing that element. For example, if we want to find out the minor for this particular element, then we have to eliminate the row and column containing that element. Then the determinant of remaining elements will give the minor for this particular element. To get cofactors from minors, we have to put appropriate signs for minors. How we will put these signs? For the elements occupying in the even positions, we have to put positive signs. Similarly, for the elements occupying in the odd position, we have to put negative sign. So, the cofactor value for the element in the first row and first column, that is C11, is determinant of x2, x3, y2, y3. Here the sign is positive. Why it is positive? Here the position value is 1 plus 1, which is 2, which is an even number. Therefore, we put a positive sign. That is x2, y3 minus x3, y2. Similarly, for the second element, the cofactor value is determinant of x1, x3, y1, y3. But here the sign is negative. Why? Because the position value is here 1 plus 2 is 3. 3 is a odd number. Therefore, we put a positive sign here. Similarly, we can find out the cofactor values for remaining all elements C21, C22, C23, C31, C32, C33. Then the cofactor matrix is given by arranging these cofactor values in a matrix form. That is, C is equal to x2 y3 minus x3 y2, x3 y1 minus x1 y3, x1 y2 minus x2 y1, y2 minus y3, y3 minus y1, y1 minus y2, x3 minus x1, x1 minus x3, x2 minus x1. But our concern is the transpose of cofactor matrix. What is transpose? Transpose of a matrix is given by the interchange of rows and columns. So we have to interchange the rows and columns of this cofactor matrix. Then we will get the cofactor matrix transpose, which is given by this matrix. Okay. Then we have to find out the determinant of that particular matrix. Determinant of that particular matrix will given as x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1. Then the inverse of matrix D is given as 1 by determinant of that particular matrix into transpose of cofactor matrix. On substitution, we will get D inverse is equal to 1 by x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1 into matrix x2 y3 minus x3 y2, y2 minus y3, x3 minus x2, x3 y1 minus x1 y3, y3 minus y1, x1 minus x3, x1 y2 minus x2 y1, y1 minus y2, x2 minus x1. This denominator is little much difficult to remember, so we can replace this denominator with a easier term. For that, consider the area of this triangular element whose vertices are x1 y1, x2 y2 and x3 y3. We know that for the area of a triangle, the equation is half into determinant of 1 x1 y1, 1 x2 y2 and 1 x3 y3. On expansion, which will give area equal to half into x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1. For we will get x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1 equal to 2 into area of that triangular element. Therefore, we can substitute this expression in the earlier expression. Therefore, the equation for L1, L2, L3 will reduce to 1 by 2a into x2 y3 minus x3 y2, y2 minus y3, x3 minus x2, x3 y1 minus x1 y3, y3 minus y1, x1 minus x3, x1 y2 minus x2 y1, y1 minus y2, x2 minus x1 into 1xy. This is the final expression that we need. That is the expression for the natural coordinates L1, L2 and L3 in terms of x and y. We can expand this matrix and find out the expressions for L1, L2 and L3, which will give L1 equal to 1 by 2a into x2 y3 minus x3 y2 plus x into y2 minus y3 plus y into x3 minus x2, and L2 equal to 1 by 2a into x3 y1 minus x1 y3 plus x into y3 minus y1 plus y into x1 minus x3. Then L3 equal to 1 by 2a into x1 y2 minus x2 y1 plus x into y1 minus y2 plus y into x2 minus x1. This is the final expression that we needed. That is the expression for natural coordinates L1, L2, L3 in terms of x and y. Now we can find out the values of natural coordinates L1, L2 and L3 at the node point. At the point A, when we substitute x equal to x1 and y equal to y1, we will get L1 equal to 1, L2 equal to 0 and L3 equal to 0. Similarly, at the point B, when we substitute x equal to x2 and y equal to y2, we will get L1 equal to 0, L2 equal to 1 and L3 equal to 0. Similarly, for the point C also, we will get L1 equal to 0, L2 equal to 0 and L3 equal to 1. Thank you for watching.